Alright, today we're going to be talking about transformers. So, what is a transformer? Transformers are used in almost every electrical system to either step up, step down, or isolate one voltage level from another. They are used to do this safely and efficiently. By definition, a transformer is an electric device that uses electromagnetism to change voltage from one level to another or isolate one voltage from another. An example of this is transformers are used to increase generated voltage to a high level for transmission across the country and then decrease it to a low level for use by electric loads. So here's a picture of a transformer. You can see that there's the primary winding and the secondary winding. Transformers have a primary and a secondary winding. The primary winding draws energy from the source. The secondary winding delivers the energy at the transformed or changed voltage to the load. So depending on if it is a step up or step down transformer, the turns ratio on each winding is going to vary. The turns ratio of a transformer is the ratio of turns in the primary winding to the number of turns in the secondary winding. For example, you have a step up transformer. That means that twice the voltage is induced on the secondary. The turns ratio would be 1 to 2. So on the left side, on the primary winding, there would be less turns ratios than on the secondary winding. So it would be thinner on the left, thicker on the right. Side note, power is equal throughout the transformer. It does not gain voltage. Because power is equal to voltage times current, and power is always equal on both sides of the transformer, the voltage cannot change without changing the current. Example, when voltage is stepped down from 240 to 120 volts in a 2-to-1 ratio transformer, the current increases from 1 amp to 2 amps. So if you decrease your voltage, your amperage is going to go up. If you decrease your amperage, your voltage is going to go up. It's simultaneous. Voltage and current may be changed, but power remains constant. So here are examples of step-up and step-down transformers. You can see that on the step-up transformer, you're stepping up from 110-120 volts to 220-240 volts. And you can see that on the left side, it's a lot thinner than on the right side. Vice versa, on the bottom, you're stepping down from 240 to 120. So your primary coil is going to have more turns in it than your secondary coil. Here is an example of an industrial transformer. It's worth noting that in the industry, one main advantage of increasing voltage and reducing current is that power may be transmitted through smaller gauge wire, and that reduces the cost of power lines. Let's talk about transformer losses. Transformers are not perfect, and not all the energy received by the primary windings gets transferred to the secondary windings. So what's the main cause of energy loss in electricity that we know from almost every class? Heat. We always lose energy in the form of heat. There are 3 different types of losses in an iron core transformer. They are resistive, eddy current, and hysteresis loss. All of these losses make the transformer hot while it operates. If a transformer is overloaded and defective, you will be able to tell by smelling burning insulation or seeing smoke or seeing color changes on the casing of that transformer. This was just very important for me to say that transformers have no moving parts. No moving parts. So let's go over some of the losses. Resistive. That comes from the resistance of the coil winding. When current passes through a winding, the winding heats up and loses energy that could have been transferred to the secondary. Eddy current. Iron is a fair conductor of electricity. The varying magnetic field that induces a voltage in the secondary of a transformer also induces small voltages in the iron core of the transformer. They can be minimized by making the core out of thin sheets, also called laminations, that are insulated from each other, or by using powdered iron cores instead of solid blocks of iron. hysteresis results in heating of the iron core, can sometimes be referred to as magnetic friction, can be minimized by using high silicon steel and other alloys in the core. Transformer connections. Transformers can be connected in different ways depending on why and where they are needed. They can be connected in either single-phase or three-phase. You will find single-phase connections in residential areas, while three-phase connections will be found in commercial and industrial settings. Another side note, high voltage windings will be marked with H1, H2, etc. Low voltage windings are marked with X1, X2, etc. That's an important note because you'll see some of that in your lab. Single-phase transformer connections used in residential applications. Electrical service to dwellings is usually single-phase, 120 to 40 volt. 120 volt is used for general purpose receptacles, outlets, and general lighting. 240 is going to be used for your larger appliances, heating, cooling, cooking, dryers, washers, etc. Three-phase transformer connections. Three-phase transformers are connected to develop three-phase voltage. May be connected in Y or delta. Sorry, I said the first one wrong. 3 single-phase transformers are connected to develop three-phase voltage. In Y connection, the end of each coil is connected to the incoming power lines. That's your primary side, or used to supply power to the load, secondary side. The other ends of each transformer are connected together. In delta connection, each transformer coil is connected end to end to form a closed loop. Control transformers, this is what we're going to be seeing in our lab. A transformer that is used to step down the voltage to the control circuit of a system or machine. Most common control transformers have 2 primary coils and 1 secondary coil. The primary coils of a control transformer are crossed so that metal links can be used to connect the primaries for either 240 or 480 volts AC. Most of the time they are used to reduce the main or line voltage of 240 or 480 to a control voltage of 120. To obtain a control voltage of 120 volt AC from a line voltage of 240, the 2 primary coils must be connected in parallel. This would be an example of stepping down 240 to 120. To obtain a control voltage of 120 from a line voltage of 480, the 2 primary coils must be connected in series. An example of stepping down 480 to 120. So here is, see if you can see it like that. Yeah, you can. Okay, so here is an example of the control transformer wired in series. So H1, H2, H3, X1, X2, those are your connection points. So that's where you would be wiring in your terminals at. So stepping down from 480 to 120, you can see that you're connecting H2 and H3. So both windings on that transformer on that side of the transformer are in series. It's all one series wired. It's wired up in series. And so I wrote a little side note down here. What do the X and H stand for? We need to reiterate that. H stands for high voltage. X stands for low voltage. So you can see that on your high side that they are labeled H. On your low side, they are labeled X. Alright, and this is parallel. So if you want to step down from 240 to 120, you would have to wire up H4 to H3 and H2 to H1. And that would be in parallel because it's 2 separate windings, as you can see from the picture. So, just a summary. We went over step up and step down transformers. For the lab for this week, you're going to be wiring up a control transformer. That information will be in your pre-lab, and you need to complete the book work for this week as well.